Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. I first want to apologize because I don't have nice printing there. Normally I would, but I forgot on my PDF that I work off of to actually leave a page for me to derive this topic. And so I just needed a blank page and I hand wrote it here. If you're one of my students, you already have the printout clean. But anyhow, we're going to be talking in this video about probably the most important topic for the rest of calculus for any calculus student, not just for one of my students, but all calculus students. This is one of the most important ideas that you can, if not the most important idea in all of calc from this point forward. All right, let's talk about it. A Riemann sum. Well, without actually telling you what it is, let's talk about what we talked about in the last video, which was finding areas underneath curves. And we developed this idea. And the idea was as follows. Somebody hands me a function on a closed interval from A to B. So I'm just going to map out some function here. It's not that big of a deal what it looks like because the mindset will be the same no matter what. So here's a continuous function on a closed interval from A to B. By the way, it doesn't even need to be continuous, but it'll be continuous for this conversation. And what we did in the previous videos, we broke up that interval into a bunch of little sub-intervals, bunch of little sub-slices. So let me just go ahead and write down all the information we're doing here. We're going to break that interval from that closed interval from A to B into n sub-intervals. And in the previous video, we broke it into 4 subintervals, but now we're just going to keep it arbitrary. So we just break it into n subintervals. Let me just showcase really quickly what some of the first few steps of these subintervals might look like. All right, so that's what it kind of looks like. Those dot dot dots mean that we keep slicing and slicing, but there's n subintervals. One thing I want to mention here is that for our purposes, we're going to make them equally spaced subintervals. When you move into advanced mathematics, so if you do some applied mathematics in advanced mathematics and stuff like that, these subintervals do not need to be equally spaced. And in fact, it's probably not best in applications to have them equally spaced. But for our purposes and for the development of the rest of calculus, it is important that we say these are equally spaced subintervals. Well, if you divide that interval from A to B into n subintervals, each subinterval will have the same width. So I'm going to note here, as a second little note here, the width of each interval or subinterval is delta x, that's what that little triangle is that I kind of sloppily wrote there, is equal to b minus a over n. So if our interval started, let's just pretend, at 1 and ended at 20, and we did 19 slices, well, 20 minus 1 is 19. Divide that by 19, and each slice has a width of 1. Okay, so that makes sense, right? So that's why each subinterval has this width to it, delta x equals b minus a over n. That is very important to memorize, very, very critical. Also, we would love to name these points. Naming these points is very important as well, because from our previous video, when we found out how to approximate the area underneath a curve, we ended up evaluating a function at these heights here. Right? So we were evaluating a function at each of these little heights. And so it's important for us to have x values for those. So let's label the x values. Tradition is that the first value, a, is titled x sub 0. X naught is what we would call that, x naught. The second x value would be x1, and then x2, and x3, and x4, so on and so forth down the line. You will end when you have n slices. Let me just convince you of something. If I had an interval, excuse me, if I had an interval start at A and go to B, and I only did 2 subintervals. Well, obviously this is x0, that's x1, and notice where we would end, x2. I had 2 intervals, we end at x2. So if I have n intervals, I will end at x sub n. So let me write that in here. This is going to end at x sub n if I get my pen working. There we go. And therefore the point right before that, this point right here, is x sub n minus 1. This point is x sub n minus 2. And this point is x sub n minus 3, and so on and so forth. Now there's also, it's also very important to talk about an arbitrary slice in here. The arbitrary slice is very, very important to talk about because most of the time you're going to be dealing with the arbitrary slice. So let me draw in an arbitrary slice here. That arbitrary slice that you see right there, this little sliver of slice of bread or whatever you want to call it, we're going to say that that goes from one x value, let's say x sub 10 to x sub 11, right? x10 to x11, or maybe it goes from x20 to x21. Whatever they are, they're neighboring x values. And we generally do this. We say it goes from x sub I minus 1 to x sub I. Again, that's x sub I minus 1 to x sub I. And this would be the ith slice. Let me write that a little cleaner. Ugh, my hand is causing this thing to jump around. This would be the ith slice. We call it the ith slice because if you go over here, this obviously should be the first slice, and this should be the second, and so on and so forth. And notice that index first matches with its right edge point, x sub 1. The index second slice matches with its right edge point, x sub 2. And so when I look at the ith slice, its right edge should be x sub I. So that's just a heads up. That's our arbitrary slice. So what have we done? We've been given a function defined on a closed interval from a to b. We've broken that interval a to b into n subintervals. The width of each subinterval is delta x, which is b minus a over n. And by the way, all the x values we could easily label this way. X sub I, the ith x value, whether it's the first or the second. In fact, let me justify it this way. X sub 0, well, that's just x sub 0. It's equal to a. X sub 1, well, to get to x sub 1 from a, I would add 1 step. Remember, delta x is our width of each of those slices. So to get from a to x sub 1, I would step by 1 step of delta x. Well, if I wanted to get to x sub 2, I could start at a and take 2 steps of size delta x. Start at a and take 2 of those step sizes of delta x to get to x sub 2. If I want to get to x sub 10, I would take 10 step sizes. And in general, let me erase all this so that I have it very clean. In general, the ith x value is given by a plus I steps of size delta x. That's a critical equation as well. So let me box up these two very, very, very critical equations there. You'll need to know what delta x is, and you'll need to know what x sub I is. Great. So far, so good. Now, let's suppose that we want to add up the area over this entire interval from a to b. We want to approximate the area underneath this curve. We could use left edges like we did in the last video, or right edges, again, like we did in the last video. Let's suppose that we use right edges. Why not, right? So let's use right edges here, and I'll use red for the right edges. So in the first slice, I have that right edge there, gives me a cap, and now I can find that area, right? And the second slice, its right edge will give me the height of that slice, and I can find the area of that rectangle. And the third slice, I'll use its right edge, again, to find the height of that slice so I can find the area, and so on and so forth, all the way through this whole entire list of slices, including the ith slice, right? and all these other slices throughout. So I'm just going to quickly do this. There we go. Okay. If you have enough slices, the area that you're trying to approximate should be pretty decently approximated if you have enough slices. Maybe like 1,000 or something like that, which you don't want to do that by hand, obviously. So to approximate this area, we need to add up all these slices. Well, this is where the ith slice comes into play. The area of that ith slice is the following. Area of the ith slice, maybe I should write that down actually in language first. The area of the ith slice, which we're calling a sub I, is going to equal, let's see, the height of that slice. Well, the height of that slice is actually f at the right edge there, because we're using right endpoints. So it'll be f of x sub I, and maybe I'll even say height times width, but that's f of x sub I. And the width, well, the width of every single slice is the same here. Remember, we labeled the widths of all those subintervals as delta x. So I'm just going to say f of x sub I times delta x. That's the area of the ith slice. Well, how many slices do we have here? Let's see, I have the first slice, the second slice, the third, the fourth, and so on and so forth, all the way until we get to this slice, the nth slice. So we have n slices. So let's go ahead and sum up these areas. And this brings into play your pre-calculus concepts of summation notation. So we have the sum. That's what the capital sigma is there for, is to say I'm about to add a bunch of stuff up. And we're going to sum up all these areas. In fact, maybe I should write it backwards. I'll say, we'll sum area 1 plus area 2 plus so on and so forth down the line until you get to the nth area, the area of the nth rectangle. And a better way to write that is that sigma notation. Sigma notation, we're going to start at I equals 1 and go to n, and we'll sum a sub I. In other words, when I is equal to 1, we have a1 plus, and then the index I increments up to 2, and we're going to add a sub 2. And then it increments to 3, and so we add a sub 3. Until we get to n, we add a sub n. But we've just written a formula for the ith slice, and that's why that ith slice is so incredibly important. The formula is height times width, or f of x sub I, times delta x. Well, let's go ahead and write that down. So this is a summation I equals 1 to n of f of x sub I times delta x. That is an incredibly important formula. That's called a Riemann sum. And it's so important in all the rest of calculus that you can't avoid using it. You have to use it. Otherwise, you're not taking calculus. That's just how it works. So let's take a look at everything here. We have a function that's defined on a closed interval. We break that interval into n groups. Each group has a width of delta x, which is b minus a over n. We label all the x values so that x sub I is just a plus I delta x. We can find that at any given moment. And then we know the sum of the areas, if we're using right endpoints, is the summation I equals 1 to n of f of x sub I times delta x. If, by the way, you were using left endpoints, so let me just make this mention here, that this is the formula actually for the right endpoints. We've added up a bunch of right endpoints. What if we instead wanted to add up the left endpoints? Well, I'm not going to redraw all this stuff because I don't want to, but instead I'll just look at the ith piece there, the ith slice. If I were to use the left endpoint to give me the height, then the area of that ith slice would be the function value, well, the height times width. Maybe I should start there. It's height times width. Height of that ith slice times the width of that ith slice. The height of that ith slice is f evaluated at x sub I minus 1. So that would be f of x sub I minus 1, and its width is still delta x. So using that as the baseline for our Riemann sum, rather than f of x sub I, we're doing f of x sub I minus 1. That's the only difference between the two. So it's a summation, I equals 1 to n, same summation, f of x sub I minus 1 times delta x. Those are the right and left endpoint methods for approximating the area underneath the curve, and that summation, this one's in particular, is called the Riemann sum. And now I can go to my first official page. So there we are. If f is defined on a closed interval, this interval has been split into n subintervals, and each subinterval is just x sub I minus 1 to x sub I for I equals 1 to n. And if x sub I star, and we'll talk about that in a moment, is some element between x sub I minus 1 and x sub I, then a Riemann sum of f is defined to be this. S we use here because I'm not telling you that we're using right or left endpoints. I'm just saying we're summing up a bunch of heights times widths. But when you specifically choose a left endpoint, that becomes L sub n. If you specifically choose a right endpoint, it becomes R sub n. And finally, the delta x sub I is a constant which depends upon I. And for our purposes, again, in calculus, that delta x sub I will not actually depend on x sub I or on I. Instead, it'll depend upon the number of slices, and it'll always be equally spaced. So you could just kind of not think about that sub I as being there. However, the rigorous definition is truly with that I there. But in reality, until you're in upper division mathematics, they're all the same widths. All those slices are the same widths. And so it's just b minus a over n. And I think I write that somewhere else, but if I don't, I will just say it right here. Delta x is equal to b minus a over n for us, and x sub I is equal to a plus I delta x. All right. The elephant in the room is going to be this x sub I star. You're going to say, wait a second, you just did this whole derivation of this, and you didn't have a little star on your x sub I. You just said that this was going to be f of x sub I without a star. I did. However, there are an infinite number of methods that you can use to grab an element, a test point, or a sample point within your interval. Let me hop back and show you. So in this problem that we were working on, or in the derivation, we used the right endpoint to derive a formula, and then we used a left endpoint. But there's nothing to stop us from deriving a formula using the halfway point, or the quarter point, or the 3/4 point, or the 1/10 point, right? So there are a lot of other points you could have used as your test value for the height. So whatever point you decide upon in that interval to use as your test point, that will determine the height in that interval. So if I did decide to use, for example, the 1/10 point, then I'm putting a top on my rectangle at the 1/10 of the way through that interval. That's all. So again, that's why when I wrote my formula, or typed out my formula, I had an x sub I star because of the fact that I don't know what point you're going to pick within that interval from x sub I minus 1 to x sub I. Again, x sub I star is just some number between x sub I minus 1 and x sub I, and it could actually be the right endpoint or the left endpoint or halfway through or 1/10 of the way through, whatever you want. And just to bring it back around, that's exactly why I have that x sub I star there. Generally in Calc 1 and Calc 2, you'll be told to use either the left endpoint or the right endpoint or a midpoint. And like I said earlier, we'll get around to midpoints, so don't really freak out about that. They're actually not too bad. But the most common initial forms of Riemann sums are the following. The two that I've written down on the previous page. R sub n is equal to the summation from 1 to n of f of x sub I times delta x. Remember, you should always think of these as heights times widths. and heights times widths, because that's all they are. You're adding up just a bunch of heights and widths. That's it. And then there's the definition where delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. Notice right now, I'm not really giving you a concrete, let's compute this example, because that's reserved for the next video. This is the theoretical derivation of a Riemann sum. The final statement I want to make here before we take a break and close out this video is that the true area under the curve can be found by taking the limit of that Riemann sum. So again, if f is defined on the closed interval and the signed area between f and the x-axis, well, not if, then the signed area between f and the x-axis on the closed interval from a to b is the limit as n goes to infinity, as our number of slices tends to infinity. And that was what I showcased in the previous video with that animation. I'll go ahead and bring it back here to close out this video, but that's what I was saying in the last video. You increase the number of slices, you get a better and better approximation for the area underneath the curve, and eventually you limit to the area, the true area under the curve. So here we are, I'm just doing a different function, e to the x here, and I've cut it into two slices. Obviously, from 1 to 2, by the way. Obviously, that's a terrible estimate of the area between the function and the x-axis, or underneath the function and the x-axis. Terrible, terrible estimate. But as I increase the number of slices, all of a sudden we get to a really good approximation of the area. Again, I'm not telling you what that area is right now, because I don't want to, but I'm just giving you the visual of this for right now. We're developing a concept, but I hope that makes sense. The finer the slices, then the better your approximation for the area underneath the curve. If I zoom in, you see those little rigid edges are there. That's because we only have 50 slices. If I had 1 billion slices, there would not be those rigid edges.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.